This video covers Kirchhoff's laws. So now we're getting into the real circuits. This first part is called equivalent resistance. This means that the total resistance of two or more resistors in a part of a circuit or in the entire circuit can be replaced with an equivalent resistor. Again, I can take these two out and replace it, and everything else would stay exactly the same. So here are very simple examples. Again, two resistors in series. We know that they are in series because there is one path from the beginning to the end. So here we can simply add them together to get a 6. And again, this is the one that we want to focus on. When you have two resistors that are in parallel, again, I know they're in parallel because there are multiple paths. So again, here I have a junction. So I can take one path here or another path here, and then at the end they do meet up. So for these, I need to add them 1 over 2 plus 1 over 4. Remember, when you're adding fractions, you don't add the bottom one, you find a common denominator. So you get 3 over 4, and then remember to find the inverse to actually get the equivalent resistance. Now we're going to Kirchhoff's first rule. This is called the loop rule. This is one of the most important rules for circuits. This means that the potential difference in a loop of a circuit is 0. What that means is that you're going to add up all those potentials in a circuit, and they have to add up to 0. This is based on the conservation of energy. Again, potential, like potential between plates, is independent of the path. So it doesn't matter if I go from here to here or here to here. The potential difference across these 2 points is still the same. So when I put a charge at those potentials, then I get potential energy. So again, based on conservation of energy, I have to have a potential difference of 0 if I go from here and back, regardless of the path taken. So for this part, you can go ahead and read if you'd like. For the most part, we're going to consider voltage analogous to height and gravity. So resistors or other electrical components are going to have negative potential, whereas batteries and generators usually have positive potential. But it's actually possible for us to have negative potential with batteries and generators also, but we'll see examples of that in a bit. Again, batteries or generators are known as electromotive force. These are providing the positive potential difference for my circuit. So positive potential difference, positive EMF, is assigned to the strongest battery, and negative potential difference is assigned to any reversed or weaker batteries, and we'll show an example of that next. Again, Kirchhoff's loop rule says that all of our potentials in a circuit have to add up to 0. So we're starting on our strongest battery, in this case only 6 volts, so that's our EMF. And as we go through my circuit, I'm going to lose some potential or have a potential drop. So across my first resistor, I have a negative VR1. Across my second resistor, I have a negative VR2. And across my third resistor, I have a negative VR3. So again, they have to add up to 0. That means the potential across the first resistor must be 2. Same thing here, we only have one path all the way around. So we're going to start on our strongest battery, in this case 12 volts. We're going to drop some potential across R1. And then if you notice the way the second battery is oriented, I have a negative here and a positive here. So if my path is to go from negative to positive, remember that I have an increase in potential. I'm going from a low to a high. So that means I'm actually going to add that potential. But when I go across my second battery, I still have a drop in potential. But when I add everything up, I still need to get a value of 0. So with that information, I can figure out that the potential across my first resistor must be 14. Here we have the same situation, except my battery has now been flipped. I now have the positive on this side and the negative on this side. So when I go across this battery, I'm actually going to decrease in potential. So you see here that I have a negative instead. But again, adding them all together still have to give me 0. So that means my potential across my resistor 1 is now 6 volts instead. Here I have 2 separate loops. So if I go across the first loop, then I'm going to follow what I've written here in blue. Again, my potential through this one loop still has to give me 0. So if I have 12 in my battery, I must lose 12 as I go across that first resistor. If I look at the loop in red, I follow here what I've written in red. Again, the potential across my battery minus the potential across this one resistor in that red path still has to give me 0. That means the potential across this other resistor is also equal to 12. Now we come to Kirchhoff's junction rule. This says that the current entering a circuit junction must equal the current leaving the junction. So, current in equals current out. Remember that a junction is where my path splits, like in resistors that are in parallel. Remember that current is equal to charge over unit of time, so think of these as my actual electrons traveling through my circuit. If I have a certain number of electrons coming into a certain junction, that's the amount I have to have come out of my junction. That means that at one point, I cannot have a number larger than my total. So 3 and 3 could be one solution, or I could have 5 and 1. It just depends on the resistors. But current in, 6 amps, have to equal my current out, 6 amps. Again, this is based on the conservation of charge. I cannot have more or less than what I have already. Also remember that the direction of the positive current is from the positive terminal of a battery to the negative terminal. Again, we're saying that the protons are moving here, even though we know that actually the electrons are the ones that move. So again, in this example, we're looking at current. The current here is 8 amps. Now again, these are charge per unit of time. Since there are no junctions, there are no multiple paths in this circuit, the current across at each point has to be equal to 8 amps. Here we're actually told that we have two different currents, a 6 amp current from one battery and a 2 amp current coming from another battery. Again, when they meet this junction, they do add up. That means I have 8 amps that go across this resistor in the middle. But when we come to our second junction, it splits up again and we have 6 amps returned to the first battery and we have 2 amps returned to the second battery. In this situation, we only have one battery, but we have two resistors that are in parallel. Here we have 9 amps that are coming out of my battery. That means when they reach this junction, if I know 3 amps go through one direction, that means 6 amps must go the other way. Again, when they meet up at this other junction, they still have to add up to the total current running through my circuit. So if you notice, this gives us a couple of implications of Kirchhoff's rules. For voltage, when we're looking at resistors that are strictly in series, their voltages are going to add up. When we're looking at resistors that are in parallel, they will have the same voltage. Because voltage in a loop containing a power source is 0, again, based on the conservation of energy, Kirchhoff's first rule. And then again for current, which is represented by our I, for resistors that are in series, they have the same current that goes across them. Again, the charges or the electrons that pass through the resistor have to continue to pass through all other resistors. And if we have them in parallel, they are actually going to add up. Again, we said that if we have, let's say, 8 amps that go into a junction, and let's say 5 amps go this way, 3 amps must go the other way, and then when they reach that other junction, they should add up to the same amount that we had before we reached the junction. So let's try this first example. Now this one is strictly 3 resistors that are in series, and we're given that our first resistor has a resistance of 2, and our second one has 4 ohms, and our third one has 6 ohms. Now to find the equivalent resistance, this is for a circuit. To find the equivalent resistance, we have 3 resistors in series, we simply add them up. So this is my equivalent resistance. That means I can replace all of these 3 resistors with a resistor of 12 ohms, and everything would be exactly the same. Now to solve for current, remember that V equals IR. So if I wanted to solve for current, that's simply V over R gives me I, or 2. So that means that going through my wire is 2 amps. Now because these three resistors are in series with each other, if 2 amps cross the first resistor and there are no junctions, then 2 amps cross every other resistor. Again, Kirchhoff's conservation of charge. And to solve for the voltage for each of my resistor, I simply do V equals IR. So that's 4, 8, and 12. And then if you notice, all of these numbers add up to 24, which is good because if we started with 24, we have to lose all of that voltage to get to 0. Again, Kirchhoff's conservation of energy. In this other example, we have 3 resistors that are in parallel. So, to solve for the equivalent resistance, again, the resistance for my entire circuit, I have 3 resistors that are in parallel. So that's 1 over 2 plus 1 over 4 plus 1 over 6. Again, you have to make sure that you are not adding the denominators. You have to find common denominators here. And then one of the most important rules is that you do need to get the inverse of that after you've added them all together. So 12 over 11, or 1.09, is our equivalent resistance. Again, that's the resistance for the entire circuit. So that means if I wanted to, I could redraw this and replace these 3 resistors with the 1.09 ohm resistor, and then everything else would be identical. So again, to solve for current, I simply do 24 over 1.09, and that gives me a current of 22.02 amps. Again, V over R gives me I. Now again, you need to look at what your circuit's doing. If I were to take this path, that's one loop, I would have to do that voltage minus my voltage across resistor 1. Would have to give me 0. But that would have to be true for all other paths. That's not a different path. For all other paths. So that means the voltage across each of these resistors is simply the voltage of my battery. And again, solving for my current, which is V over R, gives me I. Then this is 12, this is 6, and this is 4. And again, once these add up together, I should get 22. Exactly. 22.02 is the number I got when I rounded, 1.09. And again, this makes sense if you were to check your values, that if 12 amps go this way, and 6 amps go this way, and 4 amps go this way, when they reach back up to my junction, this is the point where they all meet up again, I should get the 22 amps that I had go into that junction. So let's try putting it all together with a little bit more complex circuit. Here we have two resistors that are in series with each other, and that's resistor 2 and resistor 3. These are in series with each other. They are in parallel with resistor 4, and then all of those three together are in series with resistor 1. Okay, so if I wanted to simplify this circuit, I would first have to simplify R2 and R3. And again, you don't need to write this every single time, but it helps to kind of visualize what it would look like the first time. Again, if I simplified R2 and R3 and got R, two, 3, this is what it would look like. If I went ahead and simplified it again by combining R2, 3, and R4, then my circuit would look like this. And again, this is not a capacitor, this is a battery. And then if I wanted to simplify this one more time to give me the equivalent resistance for the entire circuit, this is finally combining R4 with R1. Okay, so let's go ahead and try this all together. So first we need to find the equivalent resistance. Again, I said we have to combine R2 and R3. So if those are in series, then we simply add them together to give us 4. And then I'm going to combine R23 with R4. Now these two are in parallel with each other. So again, that's 1 over 4 plus 1 over 2. Common denominator gives me 3 over 4. And then finally, make sure that you get the reciprocal after that. So that means that this 3 resistors have an equivalent resistance of 4 over 3. And then that 4 over 3 is in series with R1. So if I wanted to add it to it, again, I'd have to find a common denominator. So that would give me 10 over 3. And again, for the most part on the multiple choice section, you're going to find numbers that are very easy to work with. And then with all of this information, I can solve for the current of my circuit, which in this case is simply 3. Now this current is a current that's coming out of my battery. This is 3 amps here. That current crosses my first resistor, and then it splits when I get to that first junction. I don't know if it's going to split evenly, so we need to figure out other things instead. Again, if that is the current for R1, then the voltage for R1 is 6, simply using V equals IR. That means so far, I've already used up 6 of my volts. So that means I have 4 left over. That means that if I were to take this path in blue, I would have to use up the rest of those 4 volts. That means R4 has a potential difference of 4. So again, if I had 10 and I've already used up 6, then this one must be equal to 4. So if I know the voltage across that one, then I can figure out my current, which is just 4 over 2, or 2. Which means that I now know how much current has gone through my resistor on the right-hand side. So I'm going to go ahead and clear some of this up. Actually, I'll go ahead and just redraw my circuit down at the bottom. Again, we said that we now found out that 3 amps are coming out of my battery. That means when they reach that first junction, 2 are going in this direction. That means 1 has to go the opposite direction. So that means 1 goes through the first circuit and the the first resistor and the second resistor, or resistor 2 and 3. Again, 2 times 1 is 2, 2 times 1 is 2. Now you might say that these numbers do not add up to 10. Well, that's good, because we only have 10 volts to work with, so we can't go over per loop. So what instead you should be checking is that the potential through one loop, let's say this loop, the potential through this loop has to add up to 10, and then the potential through the other loop has to also add up to 10. And in fact, they do.